Hi, everyone. Thank you so much for coming to my talk. My name is Michael Roy. I'm a PhD candidate at the University of Massachusetts, Boston. And I first want to acknowledge my two collaborators, Dr. Georgia Mavramati and Dr. Jared E.K. Burns, my PhD advisor at UMass Boston. So my work is primarily at the Plum Island Estuary in Massachusetts. And this represents the longest continuous series of salt marshes in the northeastern corner of the US. It's currently threatened by both sea level rise and the range expansion of the fiddler crab Manuka pugnax north of Cape Cod, Massachusetts. Pie marshes provide important ecosystem services and functions. However, sea level rise and this range expansion have the potential to change both structure and function of this habitat. This is critically important to study because this could cascade to services, which this ecosystem provides a series of aesthetic and economic services to this community. So this is a map of Massachusetts. And as you can see, the historic range of this crab was south of the Cape. But in 2003, individuals were discovered in Scituate, Massachusetts. And then in 2014, individuals in Plum Island. The mechanism of this range expansion is a warming Gulf of Maine, which is warming at a rate that is faster than 99% of the rest of the world. So the human and natural systems feedbacks are poorly understood in this system. Dynamic modeling is ideal to understand the effects of environmental change in this ecosystem over time. And specifically, we want to understand how these two environmental threats will change the total area of this salt marsh. If the total area of this marsh deteriorates over time, this will limit the ability for this ecosystem to provide both functions and services to the species and people that rely on this ecosystem. Therefore, we built three subsystems to understand the dynamics of this system. First, we created a simplified global carbon emissions model. Second, we created a complex local environmental systems model. And we then created a complex local human systems model. We parameterized our model with the IPCC report, data from the Plum Island Estuary Long-Term Ecological Research Site, a literature review, a caging experiment that I conducted a number of years ago, and a stakeholder survey that this team conducted earlier on in this year. This is our stock and flow diagram of two of our subsystems, the carbon system as well as our localized environmental system. With the interest of time, I'm not going to go into detail within this model, but I do want to note the last two stocks at the bottom of this image, both the low marsh and the high marsh. I don't have time to go into the specifics of salt marsh ecology. If you're curious, please come and see me after this talk. But I just want to keep in mind, I want you to keep in mind that the low marsh is where this fiddler crab is occurring and may be the place where it will have the largest impact. So what we found so far is that synergistic effects are driving environmental change in this ecosystem. So sea level rise is the largest driver of environmental change, particularly as we've measured in total marsh area. So this is demonstrated in the bottom left-hand corner, which represents a plot with sea level rise only, no effects of crabs. And what we found, as you can see in the dotted purple line, which is declining over time, that on the y-axis, you'll see that that's square meters, that the total area of the marsh declines with increasing, with sea level rise over time. What's interesting is that fiddler crabs really have no effect when they are isolated from sea level rise. So they have a slight impact in a decline in low marsh area, but really no impact in total marsh area. What's really, really interesting, though, is that when fiddler crabs and sea level rise are combined synergistically, the effects of sea level rise are ramped up when fiddler crabs are present, such that the decline in marsh area happens much more quickly in the presence of crabs than when crabs are excluded from this model. So our next steps are to continue to parameterize our social model, connect it to our environmental models, and to really understand the feedbacks between these three components of our system to try to understand how functions and services will be altered over time. We welcome all thoughts, feedback, and questions, and thank you so much for your time.